Hey guys, welcome back to Pete's Garage. Well, you're at the point of your engine build, or planning your engine build, or maybe you're upgrading your engine, adding some new heads, intake, or something like that, and you're wondering yourself, what size carburetor do I really need? What should I choose? There are some basic rules of thumb, some simple formulas. I'm sorry there's math involved, but it's really pretty simple. There's some basic formulas that we can go through to give you a general idea of what carburetor you should start with. Then, once you figure out what carburetor you're going to start with, I'll help you select a little more detail about how you might tune it. Okay, that's number one. Number two, we're going to talk about, once you choose your carburetor, what kind of fuel pump do you need? Now, right now, we're just going to be talking about carbureted engines. We're not talking about fuel injection. That'll be next. So let's go through some carburetor selection. Let's go through some general rules of thumb about carburetors and how you should start choosing your carburetor, and it starts with a little bit of math. So now, before we go through the formulas, there is a couple basic things you need to understand about the engine for which you are choosing your carburetor. And that is, first is the volumetric efficiency. The volumetric efficiency is how well the engine will convert the fuel into energy. The volume of fuel has got to be converted into some form of energy. And how do you know what that is? And there are some basic rules of thumb. Now, I'm trying to give you some basics here. Of course, as I recommend through the series of videos, you want to have a machine shop or a dyno shop or somebody who you can work with through your entire build who has a lot of experience with this stuff to help you choose things, because there could be a fine line between average performance and awesome performance. So find someone to work with who's done a lot. But I'm just giving you the general rules so that if you're building it yourself, you don't have the money for a dyno guy, you don't have the machine shop guy to work, you don't have all that stuff. I'm trying to help you build it as good as you can without spending all that money. So let's get back to this volumetric efficiency. You have your car, whatever your engine is, you pull it out. It's your standard performance engine. You're just rebuilding it. Stock pistons, regular cams, standard parts. I'll say it's going to be a low performance engine. Low performance doesn't mean bad. It just means it's a standard rebuild, stock parts. So we can call it stock performance. An engine like that's going to have a volumetric efficiency of roughly about 80%. Okay? So now let's say you step it up. You get some better heads, valves. You get a higher performing cam with the heads, the manifold to match. You get to put headers on it. You step up the performance of your engine by adding better components. You get it balanced. You have a balanced rolling assembly, roller, whatever you're going to do to make it better. So now you're going to get into a high performance range. A high performance engine is going to have a volumetric efficiency of about 85%. So you pick up 5% by making a high performance engine. A full race engine, and these are engines where you're spending $20,000, $25,000 on parts, and this is a super highly tuned engine. Okay, it's a full race engine designed for drag racing or whatever kind of racing you're doing. You'll get up to about 95% volumetric efficiency. And then, almost killed myself. Not really. Then we're talking about an engine that's perfectly tuned. A perfect tuned engine is one where the pistons, the rolling assembly, the pulse that's going to be generated through the compression ratio, the intake, how that wave, remember from the intake manifold video about theory, the pulse of the intake, the velocity of the fuel, the flow through the heads, how the flow is going to go through the cylinders, how that's going to be generated, the exhaust. If the exhaust is chosen, there's no restrictions. There's the length of the exhaust is chosen for the pulse wave of the exhaust, so it's perfectly tuned. Everything from the carburetor through the exhaust, ported heads, polished, weighted through the rolling assembly, out through the exhaust, everything is chosen and it's perfect. You'll get a volumetric efficiency of 100%, maybe even better. It can be a little bit better. So that is our starting point for choosing a carburetor, understanding or deciding where your volumetric efficiency is. And it's really pretty simple. I mean, don't try and cut fine lines by saying, if I choose this piston versus this piston, that's really not going to launch you into the next category. Just keep it general. Standard rebuild, high performance parts, all-out racing, or perfectly tuned. And the difference in money, if I had to put a number to it, because a lot of people ask about money, how much would this cost? Standard rebuild engine, let's say $1,500. High performance engine, like the one I'm building for the series, that 351 408 stroke motor for the Cobra. High performance, talking about $15,000. Full race engine, drag racing, ready to roll, 30 to 50 grand maybe. Perfectly tuned engine, now you're getting up in the $100,000 range. Those are like NASCAR engines, perfectly tuned engines. That's about the price ranges you can expect. So don't cut hairs and try and decide, well, you know, if I get this manifold, can I get better efficiency? Just keep it general, because the formula we're going to go through next, all you need to know is general volumetric efficiency. Okay, so here's our formula. It's a CFM equals the CID, or the cubic inch displacement, times the RPMs, RPM at which max torque is achieved. So you need to know the RPMs, times your volumetric efficiency, divided by 3456. So let's say you're building a small block Chevy 350, a 383 stroker, or 383 cubic inches, and it's going to achieve your maximum RPM or maximum torque at 7,000. You just plug in the formula, 383 times 7,000 times 0.85 divided by 3456 comes out to a CFM of 659.4. There's another formula, there's an alternate formula, which is your cubic inches divided by 2 times RPMs divided by 1728 times your volumetric efficiency, but the number comes out to be exactly the same. So you're saying to yourself, that's fantastic, that's great, I got my number, but I can't go in a catalog and buy a Holley 659.4 carburetor. So there are variables we have to consider. So let me show you a couple things. A chart based on RPMs, max RPMs and cubic inches and what size carburetor can be. And then I'll make another chart and we'll talk about how you can decide, should I get a 650, a 700, you know, which way do I go? Which carburetor do I need? And how am I going to decide which one to buy? Now when you're measuring your carburetor and how it should be performing at wide open throttle is when you're achieving the vacuum necessary for the maximum amount of torque of the engine. So based on that and looking at your shift points, so depending on where you plan on shifting your engine for optimum torque, here is what size carburetor you're going to want to choose based on the cubic inch displacement of your engine. Okay, and here we have along the top it's 5,000 to 5,500 RPM for your shift point, 6,000 up to 6,500, 7,500, and over 7,500. Those are your shift points. Okay, and here's your cubic inches. We have 250 to 380 cubic inches. If your shift point is between 5,000 and 5,500, you want a 500 to a 650. And going down, a 390 to a 427, 650, a 428 to 500, 750, 502 to 540, and 850, and at 600 plus, you're going to want a 950. And you can look at this chart. I'm not going to read all the numbers to you, but basically, this is how you would start with your carburetor size based on the shift point, RPMs, of the car when you shift, or of the vehicle when you shift, and the cubic inches. Wide open throttle is the key. So we're going to talk really quick about what happens at wide open throttle with vacuum. And this is where you're going to, let's say you're stuck between a couple carburetors. Well, we're going to measure the vacuum. I'm going to show you what the vacuum measurements are and how you make adjustments to the carburetor to compensate for the differences in the vacuum. So let's look at the same 350 small block Chevy. And let's say you have a 750 on a duplane manifold, which will have a strong signal. You have a strong signal because the pressure drop inside a dual plane manifold is stronger than a single plane manifold. Since the velocity is different, and if you remember in the intake manifold video I talked about velocity of fuel, and which is very important to the vacuum signal or the vacuum pressure drop inside the manifold. A 750 dual plane manifold with a strong signal will probably get down the track or get you quicker in the end if you put a 650 on a single plane manifold with a lower signal because of difference in the fuel velocity and the pressure drop inside of the intake manifold. Now the important thing is the signal, a strong signal, a vacuum signal. The vacuum signal is what tells the carburetor how to react. And the carburetor reacts by atomizing fuel. And there's two things to remember, or two things that are important in that regard. First, you have your fuel shear. The fuel shear is the atomization of the fuel, or the mixture of the fuel and air, to atomize it so it can be burned. There's also fuel plating. Fuel plating is also referred to as dropout or puddling. This is when, if your vacuum drops below a certain point, there won't be enough, the pressure won't be low enough for the fuel to maintain the atomization, so the fuel will and the air will separate, the fuel will collapse, it'll become heavy, it'll drop out, it'll puddle on the bottom of the manifold. What will end up happening is you'll get a hesitation because there's puddling of fuel, and then it'll take, by the time you hit wide open throttle or you get going again, it'll take a while for that fuel to get sucked out or burned out of the manifold. It's got to get picked up, it's got to get sucked through, and you have to create a lot of vacuum to pull that off the manifold floor and force it down the heads. So the design of the head is very important, which is why I'm saying this is all connected with the manifold and the head, because that vacuum that's created is going to determine which size carburetor you need at the maximum RPM where max torque is achieved. And this is all done on a dyno. So you're saying to yourself, okay, I don't have a dyno, I'm not going to pay someone to do it on a dyno, and all the stuff you're talking about is just way too confusing, and I wish you'd make it easy for me to understand and how to tune my carburetor myself. What you're basically looking for is if you have a carburetor and it's in your car and you want to make sure that it's functioning right. You get on the car, you get in, step on it, get it at wide open throttle, right to where you're almost the maximum RPM where the torque is achieved. And you should know that based on your engine. You should know where the red line is at. But where max RPM or where max torque is achieved at wide open throttle, you want to have 1.2 inches to 1.3 inches of vacuum in your manifold. So when you pick your carburetor, you pick the size, and you're going to tune it, all you have to do is put a vacuum gauge on a constant vacuum port on your intake manifold, run the gauge or put it somewhere where you can see it, get in the car, stomp on the gas, watch the RPMs. When the RPMs get to the maximum, where the maximum torque is achieved, make sure that your vacuum is around 1.2 to 1.3. Can be down to 1.1, but this is a very narrow band. So this vacuum is very important. You keep this vacuum where it is, you make sure that you won't get fuel plating dropout, or you won't be filling the engine with too much fuel. Now, all this stuff is a little confusing. I understand that, and it's really technical. Maybe it's more than you really want to know. But what I'm going to do really quick is I would like to show you just the difference in carburetors, just the basic types of carburetors, and the configurations, and just some rules of thumb. So when you do your calculation, you come up with your number, you decide, how do I know, should I go bigger or smaller based on my applications? And I have some general rules of thumb here I can share with you. So the three types of carburetors: street legal, high performance street strip, and race only. These are the differences. Street legal: these carburetors have the needed emissions hookup to make it legal. They're usually just a bolt-on replacement. It's a street legal bolt-on replacement for an existing carburetor. It has all your hookups for your emissions, and it makes it legal for emissions. A high-performance street strip carburetor, it's going to be a non-emissions. It's not going to have the same hookups. It's a pre-1966 kind of carburetor where it didn't have those kind of things. The choke on that carburetor is going to be a manual, electric, or it's going to be a hot air choke where you have the heat riser off the manifold to pull the choke closed when the engine's cold. And then we have our race only. Race only is basically what it means. It's for racing only. It's going to have certain things, so it's going to have mechanical secondaries. Those are the secondaries for the 4-barrel instead of the primaries that it runs on when you're driving. So it's going to have mechanical secondaries. It's going to be a double pumper. It's going to have 2 pumps, one of each of the bowls. It's going to have a dual feed bowl. You're going to have 2 fuel lines coming in, one to feed each of the bowls because you want to have the fuel flow. They come in ranges 390 to 830 cubic feet per minute. Now, we talk about what kind of secondaries you want on your car, and there are a couple things that you can consider. What kind of secondaries do you need? Secondaries, mechanical secondaries for higher performance racing street strip. You're going to use mechanical secondaries. Basically, the general rules of thumb for vacuum secondaries, you're going to use those when you have a rear gear ratio of 3.55 to 1 or under that. If the car weighs more than 3,500 pounds, you're going to want vacuum secondaries. And if your compression is 8.5 to 1 or less, choose a carburetor with vacuum secondaries. Now, we talked about the formulas, choosing carburetors, different types, vacuum, difference between carburetors. One thing I want to talk about before I sum it up and show you some general rules of thumb is what you want to do about the RPM range. RPM range, there's a few things to consider. So let's talk about RPM ranges. So the RPM terms that you want to be familiar with when you're choosing your carb, first is the minimum RPM. The minimum RPM is from which you will accelerate. Where is the engine going to be idling at? That's important because when the engine is idling, that's when it's its most inefficient. You want to make sure that the velocity of the fuel and the velocity of the air going into the engine is great enough to make sure that the fuel stays atomized so it doesn't plate on the bottom and a manifold. So the converter plays a lot with that. If you're going to put a converter, a stall converter, for example, a 3500 stall converter, it wants a smaller carb than a 5500 stall converter. So based on your minimum RPM and a stall converter, that can also affect the size of carburetor you choose. What else dictates the RPM range is your cam and head design. Now, when I talked about back in other videos in my cylinder head about buying your cam and your head, in the cam video talking about your RPM ranges and where the cam is at 50, you want to, where the vacuum is start to generate, you want to try and buy when you're planning and get your cam head combination so you know where the RPM range is going to be. If you're rebuilding an existing engine, you should know what cam's in there and what type of head you have so you know what the RPM range is. But in general, the larger the head volume, so if you have a head with a very large intake port volume, very big intake ports, it wants a little less carb. So that means if you do your calculations and your calculations say you should have a carburetor 623, which of course they don't make, and you have a carburetor with a huge head volume or big intake port like a Chevy, you're going to want to go down to a 600. So the RPM range is also going to dictate in your choice of carburetor. The inside the carburetor, I'm going to show you carburetor real quick and show you what the different parts of the carburetor are and how these are affected by those parts of the carburetor. So here I have a Holley 4-barrel carburetor. This carburetor has an electric choke. The choke is operated electrically and it has vacuum secondaries. If I come around and look up on top, look straight down into the carburetor, the choke right here, the secondaries which are operated by vacuum on the other side. And when I talked about fuel metering, now I'm going to open up this, I got this, see, you can see the butterfly down there, I'm going to open it to wide open throttle. See, I'm opening wide open throttle, and when it's wide open throttle, the vacuum secondary would kick in and it would open up the secondary. So the secondaries in the back are what would open up. See the secondary in the back opening up there. So when you are at wide open throttle and you stomp on it, and when I talked about vacuum signal, you have air rushing into the carburetor. Air is rushing in. As the air rushes past the fuel metering ports right here, the air rushes past here, draws a vacuum signal. The signal goes back into the float or the bowl of the carburetor for where the metering rods are, meters the fuel as it goes underneath or comes out. Let me open this back up. The underneath the butterflies are where the atomized fuel enters the intake manifold. So at minimum RPM, you have low vacuum, and if the vacuum drops low enough, the air rushing across your fuel metering ports will not be metering the fuel properly, and that's when you get stall-out conditions and you have poor acceleration. If you're not metering your fuel, you don't have the right vacuum at idle. Likewise, when you're at wide open throttle, you want to have only so much vacuum there because you can be rich or lean based on the vacuum that is going across your metering rods. Now, inside, let me just show you this real quick. When you look inside your carburetor, you have the jets, and this is one of the jet assortments that I use. These are the jet sizes, and you can change the jets inside the carburetor. And they're by number, they change by thousands, and you can see here it goes 64, 65, 66, different sizes for the jet. And the jet inside the carburetor and you change them in pairs, so you have the left and right, but the jet is where the fuel comes out and what gets atomized, how the fuel gets atomized as it goes. You don't want to mix them up. As the fuel gets atomized through the metering rod. So when you adjust your engine and you have your vacuum gauge inside and you're going down the street, you have wide open throttle and you're at max RPM, and you don't have enough vacuum, it means you're not metering the fuel properly. You can rejet the carburetor and you can change the jets inside to make sure the fuel's being metered properly. I'm not going to get into that in the video because this is about choosing carburetor, not how to adjust it. That video would be very long on how to do that, but that's why you want to team up with a dyno guy or someone that can help you do that part. So let's close this up by just giving you some rules of thumb, and then we'll talk about the fuel pumps. Here's some more summary or some more things for you that will help you select your carburetor. Higher RPMs require a bigger carb. More horsepower, go with a bigger carb. If you have a higher compression ratio, higher than 8.5 to 1, go with a bigger carb. If you have a very high distributor mechanical advance, go with a bigger carb. Manual transmission, bigger carburetor. If you have steeper gears in the rear end, you want a bigger carb. If you have an oversized cam for the application, which is possible, you might choose an oversized cam because you want some high-end performance. So at the low end, it's going to be really inefficient, and you have to maintain your vacuum and your fuel velocity. You use a smaller carb. And also, some more information on your secondaries. Vacuum secondaries, if your car is heavy, if you have street gears, you have an automatic transmission, or you have an engine built for low-end torque, use a vacuum secondary. Mechanical secondaries, you have 411 gears or higher, use mechanical. Manual transmission, mechanical, and also if you want top-end performance, go with mechanical secondaries. Now, as you go through all this, you wonder what else can affect your choice of carburetor, or what kind of things you need to know when you go to have your carburetor tuned. Again, from the cam video, remember it's important. You know what your cam duration is at 50. That's important. The gross lift at the valve is important, choosing your carb. Your rocker arm ratio, compression ratios, your cubic inch displacements of the engine, the head type, what kind of head type you have, and the valve size, which is really, really important. If you know the flow, you need to know what your flow is through the head. Is it a big flow head? Is it a smaller port? What kind of head is it? How much is the vehicle going to weigh? The gear ratios, if you're going to have a converter, what the converter stall is in there. Do you have an overdrive? That's also important, because if you have an overdrive in your transmission, then you're going to have to choose a different carburetor because the torque curve is going to be different when you get to the higher RPMs. What's your max shift RPM going to be? Where's your red line set at? If you have a current carb, what is that? What's your current carb type? Are you going to go with the same size? You're going to change components? Do you want to change it? So if you can, you want to measure your inches of vacuum with idle timing. You want to set your timing at 30 degrees timing and check your vacuum. That will give you a good idea of what your engine is pulling with and without your vacuum line connected. So you can take off a vacuum line, cause a vacuum leak, and see what it drops, and put a vacuum line back on and see how that does. The type of distributor will just determine what kind of carburetor you need, because you need to know whether or not it has, with or without the vacuum canister, ignition box, if you're going to have a dual or single plane manifold, and the exhaust. Don't forget about the exhaust, the tube size. If you're going to have a headers, what's the tube size? You know, is it a 1 3/8, 1 1/2? The tube size is also going to have an effect on the choice of the carburetor you have. So that's most of the carburetor information. We went through the calculations. We went through different types of carburetors, secondaries, some other information about choosing it and setting up what you want to do, and secondaries, chokes, all that kind of stuff. So now all we have to do is we have to get fuel to the carburetor. Let's talk briefly about fuel pumps. Now, fuel pumps are going to be pretty simple. We got to feed fuel to our carburetor, and it's all based on horsepower and some standards. Fuel pumps. Fuel pumps are measured in gallons per hour, the gallons per hour the day they deliver. We're looking for the optimum gallons per hour that we need for our fuel pump. Optimum gallons per hour. The formula is very simple. It's the max horsepower times this brake specified fuel consumption, okay, divided by 6. This is actually a standard fuel consumption that's defined as, I'll get to that in a second. If you're doing it by liters, you divide it by 1.585 instead of 6. So if you're doing gallons per hour, you take your max horsepower times your BSFC divided by 6. If you're doing liters, do the same thing, just divide it by 1.585. Now, the brake specified fuel consumption is a standard. That is how much fuel is needed to burn to create 1 horsepower at wide open throttle. And for a naturally aspirated engine with a carburetor, you need 0.5 pounds of fuel per hour, or I'm sorry, per horsepower at wide open throttle. 0.5 pounds of fuel per hour, like I said again, per horsepower at wide open throttle. If you have nitrous oxide, it's 0.6. If you have a supercharger, it's going to be 0.6 to 0.75 for a supercharged engine. And here's the formula. Our optimum gallons per hour, let's say you have a 425 horsepower engine, and you know that because you had it dyno tested, times 0.5 divided by 6 is 35.4 gallons per hour. That is the optimum gallons per hour you would need at wide open throttle. Now, if you're burning 35 gallons per hour, that's 16 gallons every 30 minutes. You'd be driving from gas station to gas station at wide open throttle. So you're trying to plan for the maximum condition that, remember, it's calculated based on wide open throttle. So that's the formula. Pretty simple and straightforward. Now the difference is pressure. When you have a fuel pump that's feeding a carburetor, you don't need 120 psi. You don't need a lot of pressure. So whether you're choosing the mechanical or electrical, you need to also consider the fuel pressure and its relationship to the volume of fuel it's going to be delivering. And it's inversely proportional, and that is that as the pressure increases, the volume will decrease when everything is, let's say everything's equal in the engine. When you have a certain amount of fuel pressure that's always required to maintain the engine to perform, when demand is placed on it, okay? So as the demand on the engine goes up, when you step on the gas, as demand goes up, and except with forced induction applications, the amount of fuel pressure will increase. So you're going to need more fuel pressure, and the volume inside the engine will go down. So, I mean, it makes sense, right? You step on the gas, the engine demand goes up, it's going to pull more fuel, so you need more pressure to support it. It's pretty simple, but that's how fuel pumps, how you choose your fuel pump, whether it's mechanical or electric. And that's for naturally aspirated, carbureted engines only. So there you go, guys. I hope I've given you enough information to at least start picking a carburetor and deciding what's important when you want to choose a carburetor. Remember, if you're planning an engine, all the parts have to work together. The cam, the heads, the intake, the exhaust, it all has to work together, and the carburetor is an integral part of that. So maintaining vacuum, maintaining fuel velocity, maintaining the atomization of the fuel so you don't get dropout, delivering the fuel inside, the compression, and getting it out of the engine, it's all important. And it all starts with the carburetor. I hope that helps you out. If you have any questions, please leave a comment. I'll answer it as soon as I can. I really appreciate all your comments. You guys are fantastic. If you have information about choosing a carburetor, if you have expertise, you know something you can share with everybody, please, by all means, leave a comment, share it with everyone. I love reading the comments and guys that have other points of view or people that have other points of view, because there are girls out there who are doing it too. So if you have another point of view on some of this stuff, share it with us, and we're all here to learn. I appreciate all your text messages, hearing from everybody around the world, and I just want to say thanks, because you guys are really great, and it really makes my day when someone builds an engine and they have a great deal of success and they're happy about it, and they send me a text message and they have a video attached to it starting it up for the first time and showing it run. It's really, really awesome. I appreciate you watching the video, and thanks for stopping by Pete's Garage.